the topic 4.6, which is our last topic of block 4. And in this topic, we'll discuss the electromagnetic effect as well as electromagnetic induction. So electromagnetism, the topic 4.6, the subtopic is electromagnetic induction. What is the concept of electromagnetic induction? These are the learning objectives. So what is the concept of electromagnetic induction? Example, you have a wire. So example, you have a wire and this wire does not have any source of energy, like it does not have any battery or a cell, nothing is there. And it is connected to a meter. Here we connect a meter. Initially, the reading on the meter is 0. Now what happened if we move the wire either up or down? Because if we move the wire down or we move this wire up, what will happen? The movement of the wire, what it produce? It will produce change in the magnetic field. If the wire is moved up or down, there will be a change in the magnetic field. The strength of a magnetic field change. So what is electromagnetic induction? Electromagnetic induction state whenever there is a change in magnetic field, there is induced EMF. So means when we move the wire either up or down, what we will observe? We'll observe this needle will deflect either towards the right hand side or the left hand side. So definition of electromagnetic induction, whenever there is a change in the magnetic field, it will produce EMF or voltage. So without any supply, without any battery, the charges start to move because there is a change in magnetic field, and that causes a deflection in the galvanometer, or it can be an ammeter or voltmeter. So how we can change the magnetic field? There are different ways to change the magnetic field. Either I can move the magnet, moving closer or away, or I can move the wire, or I can move both of them. So if any one of this is done, like either moving a magnet or moving a wire or moving both of them, it will produce a change. And whenever there is a change in magnetic field, it will always induce EMF. EMF means like the charges will have energy or the charges get energy. So movement of the wire in a magnetic field can produce current in the circuit. That is how we generate electricity. Like how the electricity which we are using in our home is produced, it is produced in the same concept that we have coils like circular wires, rectangular wires, coils are there. And when these coils are rotated, when these coils are moved, which are connected with a turbine, so there will be a change in the magnetic field, and due to the change in magnetic field, it induces EMF. So electromagnetic induction state that change in the magnetic field induces EMF in the circuit. The EMF induced depends on two things, like the direction of the movement of the wire. If we change the direction of the movement of the wire, the induced current will also change. Example, first we are moving the wire downward. So if we are moving the wire downward, this is the direction. Example, the current is induced, current is produced. How to find the direction of induced current, that we will do in the next slide. So example, if we are moving the wire downward, the current induced in this manner. So if the same wire, if we change the direction of the motion, if we move the wire upward, what will happen? The direction of induced current will be opposite. So the direction of the current depends on the direction of movement of the wire. If we change the direction of movement of wire or we change the poles, the direction of induced current will be reversed. So if we are moving the wire downward, if the current is moving in this manner, if we change the movement of the wire, the direction of the current will be reversed, or direction of current will be changed. How to find the direction of the current? For this, we can use Fleming's right hand rule. What is the Fleming's right hand rule? According to Fleming's right hand rule, you will use your right hand. Your first finger represents the magnetic field. The index finger, the first finger represents the magnetic field. Your second finger represent the direction of the current, and thumb shows the motion of the wire, which direction the wire is moving. So example, if I apply the Fleming's left hand rule here in this figure, so when the wire example, say we don't know the direction of the current and we want to find the direction of the current, in this one we want to find the direction of the current. So we will use a Fleming's left hand rule. According to Fleming's left hand rule, try to apply that rule on the figure. Your first finger or your index finger, so the first finger should represent direction of magnetic field. And what is the direction of magnetic field? It is from north to south. So magnetic field is always pointing towards the south. So your first finger or index finger should point towards south. So as you can see in this figure, where is the index finger, where is the south is towards the right hand side. So your right hand index finger should point towards the right hand side. That is first thing. So try to align your right hand index finger towards the right hand side, towards the south. Your second finger, your second finger should point in the direction, will point in the direction of the current, but your thumb will represent the motion. Motion means which direction the wire is moving or the movement of the wire. So which direction the wire is moving? It is moving downward. So your first finger should point towards the right hand side and your thumb should point downward. So first finger is pointing towards the right hand side and thumb is pointing downward. So when you apply the rule, index finger is towards the right and thumb is downward, you will find where your second finger is pointing, that second finger shows the direction of the current. So how the current will move? The current will move in this manner. You can apply the rule. You can use your right hand, your index finger represent toward the south pole, the magnetic field. Your thumb should point downward because the current, the wire movement is downward. And where your index finger is pointing, you will find it is pointing in the arrow direction I drew. So that means this is the direction of the current. So if we want to find the direction of current, we can use Fleming's right hand rule. Apply your right hand rule here to find the direction. So this is how the direction of the current will be there. But if we change the direction of the motion of the wire, like the first case the wire was moving downward, now we are moving the wire upward. So if we change the direction of the motion, now what will happen, like if we say the wire is moving up, so again the rule remain the same but only the directions will be different. So first finger, now your index finger or the first finger which is pointing towards the magnetic field or south of the magnetic field, so the index finger, the first finger should point towards south. So that is, in this example, it is towards the right hand side, so it should point towards the right hand side. Now second finger shows the current, but we don't know the current, so we cannot align. But we know the direction of the motion or direction of the movement. So the second finger represents the direction in which the current induced or current produced, where the thumb will represent the motion or the movement of the wire. So when we apply, the wire is, the magnetic field is towards the south and the motion of the wire is upward. So when I apply my right hand, my index finger should point towards the right hand side. Your first finger or index finger should point towards the right hand side, and your thumb should point up. So when your thumb is pointing up, you will find your finger is pointing into, so with the direction in which your second finger is pointing, that is the direction in which the current is produced, and that is opposite to the initial one. So if the needle initially it was deflected towards, if it was deflected towards the right hand side first, now the needle will deflect towards the left hand side. So using the right hand rule, the Fleming's right hand rule, we can find the direction in which the current is produced, where the first finger represents the direction of magnetic field. It should always point towards the south. The thumb represents the motion of the wire, which direction the wire is moving up or down, and the second finger represents the direction in which the current will induce. And we call that as a Fleming's right hand rule. So if the magnetic field direction changes, the current direction will also change, and if the wire is stationary, there is no induced EMF. If the wire is not moving, there will be no induced EMF. Reason for that, because if wire is not moving, there is no change in the magnetic field, and if there is no change in the magnetic field, if there is no change in the magnetic field, there will be no induced EMF. So this will be at 0 mark. So if we want to induce an EMF, we should change the magnetic field. And how we can change the magnetic field is by either moving the magnet or the wire. The factors which are affecting the magnitude or amount of induced EMF: number one, the induced EMF can be increased by moving the wire faster. If I move the wire faster, it will produce greater EMF. Using the stronger magnets, if we are using the stronger magnets, magnet with greater strength, the induced EMF will also increase. And the third thing, if we use more wires or greater number of the wires, it will also induce greater EMF. Like here in this example, we are using 3 loops of wire, but the previous example we were only using 1 loop. So 1 loop will not produce too much current, but if 3 loops are there, the total current will be much higher. So these are the factors by which we can increase the value of induced EMF: by using a stronger magnet, or either by using or moving the magnet faster, or by changing the number of the turns or increasing the number of turns. So example, the Lenz law. What is the Lenz law? The Lenz law states the direction of induced EMF or induced current can be determined by using a Lenz law, that induced current always flow in direction to oppose the motion. Example, we have a solenoid. Solenoid means a circular wire. This circular wire or a coiled wire is called a solenoid. And initially there is no current because there is no supply here, so there is no current initially. So using a Lenz law, we can also work out the direction of the induced current. How we can work out the direction of induced current? According to Lenz law, the induced current always try to oppose the change in the magnetic field. So we have a magnet, north and south, and north pole is facing the coil, a solenoid. And we are bringing this north pole closer to a solenoid. So as a result, when we bring north pole closer to a solenoid, what will happen? The magnetic field for a solenoid will start to increase. If we move the magnet towards, the magnetic field will increase. So according to Lenz law, what this coil will try to do, what this solenoid will try to do, it will try to oppose it. It will try to stop it. How it can stop? So for a solenoid, north pole will be on the left hand side because like poles repel and unlike poles attracts, and the south pole is on the right hand side. So it produces a current in a direction so that it can oppose the change. And opposite will happen if the same if the same magnet, but we are moving it away. So if the same magnet, we are moving it away, now what happened for a solenoid? The magnetic field is decreasing. Because the magnet is going away, the magnetic field is decreasing. So what this solenoid will do, it will try to oppose the change. If it is decreasing, it will try to increase, or it will try to attract. And as a result, when it try to attract, how it can attract? By induce opposite pole. So south pole will be on the left hand side and north pole is on the right hand side. Because the direction of the pole changes, so direction of induced current will also change. So using a Lenz law, we can also determine which pole will be produced in a solenoid or a circular wire when there is a current induced due to a change in magnetic field. So if we are bringing a knot closer, the same pole will be induced on the side which we are bringing knot. If we move the knot away, the opposite pole will induce just to oppose the change. So if it is magnetic field is increasing, the solenoid will try to decrease. If magnetic field is decreasing, the solenoid will try to increase. Solenoid means a circular wire. So if I change, like example, instead of north pole, if I was having a south pole here. So instead of north, we have a south pole. So this is a south, this is north. So if we are bringing a south pole, what will be the pole induced here? Because the magnetic field of a solenoid is increasing. If the magnetic field is increasing, according to Lenz law, that whenever if a magnetic field is increasing for a solenoid, it will try to decrease. So how it can decrease? By producing a same pole or like pole. This time south will be here and north will be other side, and the direction of the current will be opposite. And if we move the south pole away, like we have a magnet, this is a south pole and this one is a north pole. So what pole will be induced? Opposite pole induced. Now north will be here and south, and the direction of the current will be reversed. So according to Lenz law, the EMF induced always try to oppose the change in magnetic field, and that when it try to oppose the change in magnetic field, the direction of the current will reverse. Say you have a magnet, this is the north pole, south pole, and we have a solenoid. Solenoid means a circular or a coiled wire. Example, we are moving the magnet towards. So due to the as we are moving the magnet towards, so there is a change in the magnetic field. And due to this change in magnetic field, there will be current or EMF in the coil. But which direction this current will produce? The current will produce always try to oppose the change. So if we are moving the magnet towards the solenoid, now what will happen? As we are moving it towards the solenoid, will try to reduce this effect. So how it can reduce? What pole will be induced here? What pole will be there for solenoid? Because solenoid the current produces and that will try to oppose the change. So what pole will be induced to stop it? So which pole will be induced here? Try to stop this magnet to move towards, so it will try to oppose the change. So it will have a north pole on the left hand side and south pole on the right hand side. An example, the direction of the current. Say this was the direction of the current. Example. But opposite will happen if we move the magnet away from the solenoid. As a result, when we move the magnet away, then what happened? According to Lenz law, it will try to oppose the change, as there is a change in magnetic field. But in this case, there is a change in magnetic field and magnetic field is decreasing. So what solenoid will try to do? It will try to oppose. And how it can oppose? by producing an opposite pole. So south pole will be here on the left hand side and north pole will be there on the right hand side. And the direction of the induced current will be opposite. So changing the direction in which the magnet move will induce EMF but in opposite direction. So that is a Lenz law, that EMF induced always try to oppose the change in magnetic field. Is it clear, the concept of Lenz law? Like how the exam style questions related to electromagnetic induction, how you'll find the question in exam. As in this question, the electromagnetic induction means that change in magnetic field produces EMF. We call that as electromagnetic induction. Can be demonstrated by using a solenoid. Solenoid means when we have a coiled wire with many turns, we call it as a solenoid. A magnet and sensitive ammeter and connecting wires. In a space below, draw a label diagram of apparatus set up to demonstrate electromagnetic induction. So what we have to do, we have to draw a solenoid and it should be labeled. So we will have a solenoid. Solenoid means a circular wire, a coiled wire, many turns. That's called a solenoid. Then this solenoid is connected by connecting wires, and then ammeter. What is the symbol we use for ammeter? So letter A should be there. Circle with letter A. That's the symbol for ammeter. And then a magnet should be there. Any pole it can be facing, like it can be a north pole facing or south pole. As it did not mention, so you can select any of the pole. So one side will be south, another side will be north. So this is a south pole and this one is a north pole. So this is a label, but we have to label, so we have to mention like this circular wire is called solenoid. This is an ammeter. Here is a magnet, and these are the connecting wires which are connecting. State one way of using the apparatus to produce induced current. How we can produce a current? So as I mentioned, either we move the magnet towards or away, or we move the solenoid towards or away, or we move both of them towards or away, that can induce EMF. So simple thing what we can do, by moving the magnet towards or away. So when we move the magnet either towards or away, there will be a change in the magnetic field, and that change in magnetic field induces EMF. You can also mention by moving a solenoid towards or away, that will also induce EMF. The second part, state why your method produces an induced current. So you have to explain why there's an induced EMF or induced current. So what is the reason for that? When we move the magnet, there is change in the magnetic field which induce EMF, and the current start to flow due to complete circuit. So because the circuit is complete, there is no open, like it's not an open circuit. A solenoid is there, an ammeter is there. We move the magnet either towards or away. So when we move the magnet towards or away, there is a change in magnetic field and the current start to flow in the circuit. Then the next part, without changing the apparatus, we don't want to change the apparatus. State what must be done to produce an induced current in opposite direction of original. Like we want to change the direction of current only. We don't want to change the value. but we just want to change the direction of the current. So what we should do, we should move in opposite direction, move the magnet in opposite, like if first it was moved towards the right hand side, now it should be moved towards the left hand side. So the move the magnet in opposite direction. So as a result, when we move the magnet in opposite direction, the induced current will be produced but in opposite direction as the original one. We want to produce a large current. If you want to induce large current without changing the apparatus, so we cannot, because the direction, the magnitude of induced current depends on strength of the magnetic field, it depends on the number of the coils, it depends on the speed at which we are carrying out the chain. But because they mentioned we cannot change the apparatus, so we cannot change the magnet or the coil, so only thing what we can do, we can move the magnet faster. So by moving the magnet faster, the direction of the induced current will be, the magnitude of the induced current will be larger. Is it clear, this question about the electromagnetic induction? Another question, figure 8.1 shows a bar magnet suspended by a spring over a coil. The coil is connected to a sensitive 0 millivolt meter. So basically what happened, there's a magnet is placed here. When the magnet, like when we stretch this spring and release the magnet, so magnet will vibrate up and down, like move up and down. As a result, when this magnet will vibrate up and down, there will be a change in magnetic field, and due to this change in magnetic field, there will be a induced current. And because the magnet is continuously changing the direction, so what happened to the reading of this zero sensitive ammeter? It won't stay constant, it will continuously vibrate, it will continuously change, because the direction of the current is changing. So direction, as like if the magnet is moving down, the needle deflected towards the right. If the magnet is going up, the needle will deflect left. Why? Because the direction of induced current depends on the direction of the movement of the magnet. So the lower end of the magnet is pushed into the upper end of the coil. So we push this lower end and it is held. During the movement, the EMF is induced in the coil and the meter shows a deflection towards the right and then return to zero. So first what we did right now, we move this magnet down and then we stopped. So when we move it down, we observe the needle is deflected towards the right hand side. So we observe what we observe when we are moving it down. The needle, originally it was at zero, but it deflected towards the right hand side and then it returned back to zero. So explain why the EMF is induced. So what is the reason why the EMF is induced? So when we move the magnet downward, so when we move the magnet, there is a change in the magnetic field. And because of this change in magnetic field, what will happen? There is an induced EMF or voltage. Then state what happened to the needle of a meter when the magnet is released from rest and it is pulled up. So now when the magnet was moving down, in the beginning, when we were moving down, we observe the needle is deflected towards the right hand side. So this was a 0 center voltmeter, and this is what we observe, the needle is deflected towards the right hand side. But as we release the magnet is being pulled up, or magnet is moving up. So as a result, when the magnet will move up, what will happen to this needle? If it was deflected towards the right hand side first, now it will deflect towards the left hand side. So the answer here, the magnet is released from a rest and pulled up. So what will happen to needle? It will deflect towards opposite direction, you can mention, or initially it was toward the right. So it will deflect towards left hand side. Then the magnet continue to oscillate up and down, moving in and out of the coil. With each oscillation, what will happen to the needle? So if the magnet is moving up and down, so as a result, what will happen to the needle? The needle will also oscillate, or it will deflect right and left, or it will oscillate, the needle will also oscillate right and left, because if the magnet here, which is shown, so when the magnet was moving down, the needle was deflected, the current produces, and the needle deflected towards the right hand side. When the magnet is going up, we observe the needle is deflected towards the left hand side. So as a result, when magnet is towards the right, needle deflect, going down, the needle deflected towards right. Magnet going up, the needle deflect towards left. So needle will oscillate or vibrate right and left. Is it clear, this question, that how the direction of the induced current changes as the movement of the magnet changes? So in this question, put a ring around the name of a metal that are attracted. So not all the material, like, or not all the metals are magnetic material. We have iron, nickel, cobalt. These are the magnetic material. Steel, they are attracted towards the magnet. On figure 11.1 and figure 11.2, the pattern of the magnetic field are shown on the diagram. Label the north pole and south pole. So where the field lines are pointing out, that is our north pole, and where the field lines are pointing in, that is our south pole. And the magnetic field is always from north to south. So same thing, you have to label, the magnetic field is from north to south, so this will be north pole and the other one will be the south pole. Another question, a steel bar is made of metal, suggests a metal, sorry, a bar is there, a bar magnet is made up of metal, suggests a metal. So normally we use, if it's a permanent magnet, so to make a permanent magnet, we use steel. Figure 8.1 shows a bar magnet being inserted into a coil or a solenoid, you can say. Now north and the south poles are shown for a magnet are marked. The coil is connected to galvanometer. Why the galvanometer deflect as a bar magnet is being inserted into a coil? So movement of the bar magnet, when we insert this bar magnet, it will movement of the magnet produce the change in the magnetic field, and that magnetic field will induce EMF, which caused a deflection to this needle of the galvanometer or a meter which is used here. Explain what determine the direction of the reading on the galvanometer. So how the direction is affected, it depends on the direction of the wire, movement of the, it depends on the direction of the magnet and pole of the magnet. Like if we are bringing north pole or we bring south pole, the direction of induced current will be different. Same thing if we are moving the magnet towards or away, the direction of the induced current will be different. So on what factor it depends on? It depends on the pole of the magnet, and it also depends on the motion or the movement of the magnet. Describe a method for demagnetizing a bar magnet. So what we can do, we can place in east-west direction, and we can heat or hammer, we can demagnetize a bar magnet. But that is related to the simple magnetism topic, not related to electromagnetic induction. So here the direction of the induced current depends on what is the pole we are moving. Like if I'm moving north pole, induced current will be different. If I'm bringing a south pole, induced current direction will be different. As well as it also depends on direction of the movement of the magnet, either it is away or towards. So these are some questions related to electromagnetic induction.